Okay, let's start reviewing the Assumption English School Prelim 2022 paper, which is the first prelim paper given to you in that stack of 4 papers. Now, as we go through, I will go through the answers as well as some answering techniques and extra knowledge. The extra knowledge and answering techniques are what you must learn from this lesson. All right. Now let's start. Question 1 is about chromatography. Now, whenever you're doing chromatography, you need to know what are you separating. In this case, you are doing chromatography to separate dyes in a food coloring. This is important to know. All right. So obviously, a food coloring is made up of different colorings or dyes, which can be separated by chromatography, provided the dyes have different solubilities. If the solubilities of the dyes are the same, they cannot be separated using chromatography. Okay? Now, the next thing to take note of in chromatography is what is the solvent? Now, many students will fail to underline that sentence. Ethanol was used as a solvent. This is crucial. You need to know what is the solvent used. Because later on, they could ask you, so suggest another solvent that can be used. So you need to know. All right? So in this case, ethanol was used as a solvent. Okay? Now, once you have established this, and if you understand chromatography, you will know how to do A and B. Because A, which dye is the most soluble in ethanol? The one that is most soluble will be the one that travels the furthest. Furthest from where? Furthest from the start line. Okay? So the one that's most soluble in this case is the yellow dye because it travels the furthest from the start line. Next, I believe all of you are familiar how to interpret chromatograms. To interpret a chromatogram, all you need to do is a good ruler. Okay, use a ruler and match the spots that you see. So it's quite clear cut. The food coloring will contain the blue dye. The food coloring also contains the green dye and the yellow dye. So the only dye that's not inside the food coloring is red. But the main reason why I want to go through this question is part C. Now, part C is a common prelims question from other schools. They like to test this. So what happens if you were to take a circular piece of filter paper and then you drop one drop of the mixture onto the center of the circle and let it separate? Now, if it's circular, it will not just move up like this, right? If it's circular, it will move outwards. And when the dyes move outwards, they again separate based on their solubilities. However, as they move outwards, they will move outwards in a circular manner, which means that the pattern of the blue and yellow dyes will also be circular. And the distance moved depends on the solubility. The more soluble the dye is, the further it will move from the center. So your pattern will look like this. It should be a rough circle. The blue dye will be nearer the center. The yellow dye will form a circular ring further away from the center. So this is a useful extension question to learn. Okay? So this is the same principle of chromatography. It separates based on the solubilities. The more soluble yellow dye will move further out. And the dyes form this circular pattern. So instead of just spots, now you have a circular ring corresponding to each dye. So moving on with the chromatography question, the next question is the atomic radius question. Now, you are told something called atomic radius. So whenever you are told something new, can I please encourage you to highlight or underline, since you cannot highlight in the O levels, underline the definitions. Okay, what is atomic radius? Atomic radius tells you the size of the atom. All right. On the other hand, the size of the ion is called the ionic radius. All right, so these are two different terms, atomic radius, ionic radius. So now you are given the atomic and ionic radii of the period 3 elements. All right, so you can see the period 3 elements over there, sodium, magnesium, aluminium, and so on. All right, the first thing you are asked to do is to complete the table to show the electronic structure of each ion. So this should not be super challenging. I hope we know by now the metals. The metals are the ones on the left of the period. So in this case, sodium, magnesium, aluminium, metals like these will lose valence electrons. So sodium 281 will lose one valence electron, become 28. Magnesium 282 also loses the two valence electrons, so it becomes 28, and so on. On the other hand, the right hand side, these are non-metals, and the non-metals gain valence electrons. Therefore, they go from 287 for chlorine to 288. Okay, so filling up this table. Okay, now the next question, B part 1. You are asked to state two differences between the atomic and ionic radius of the metals and non-metals. I think this is quite clear-cut. If you just look at atomic radii, the ionic radii of the non-metals will be larger. So you can clearly see that because you see, for example, Cl minus is 0.181 nanometers, but Na plus is much smaller. Na plus only has 0.102 nanometers. So in terms of ionic radii, the trend is not the same as the atomic radii. Okay, now you must get used to questions like B part 1. For many, many years, the combined science paper has not had much data based. So you must get used to this kind of questions where you look at the data, then you just simply state the trend, the difference, or the similarity. Okay, so B part 1 should still be manageable. Just look at the data. Now B part 2 is the one that is slightly more challenging, but they have tried to help you. Using the concept of electron shells suggests an explanation for your observation. So I think the easier one to explain is probably ionic radius. Why do the non-metals have a larger ionic radius? Why do they form larger ions? Why is Cl minus bigger than Na plus? So if you just look at the electronic structure, it should be quite easy to tell, right? Cl minus is 288. 288 got 3 shells. Whereas Na plus is 28, only has 2 shells. So the idea is this. Non-metals gain valence electrons to form negative ions, which will have one more electron shell than the metal ions formed when metals lose valence electrons. Therefore, the non-metals have smaller ionic radii. All right, so your answer should resemble my answer in the sense that you should make reference to the fact that non-metals form negative ions, and these negative ions have one more electron shell than the metal ions. Okay, so that's B part 2. I shall quickly show you the answer for C as well, because I don't think C is very hard. I think most of you know part C quite well, how an aluminium atom becomes an ion. Okay, so I shall leave this on the screen for you to take down for a while before I continue. Now, let's continue, but let's continue with this question. Let's not move on yet. So, we have just said metals lose electrons. Non-metals gain electrons. So I think this is an important concept for us to take down. Metals lose electrons, right? Now, if metals lose electrons, so we have learned redox and how to define reduction and oxidation. If something loses electrons. Is it reduced or is it oxidized? So lose electrons means oxidized. So metals are easily oxidized. On the other hand, non-metals will gain electrons. And by the definitions of redox, gain electrons means reduced. Okay? So non-metals are easily reduced. And this brings us to the next important conclusion. If metals lose electrons and are oxidized, if something is itself oxidized, it is a reducing agent. So metals are reducing agents. Can we please take this down? Metals are good reducing agents because they can be easily oxidized themselves. They can be easily oxidized themselves because they lose electrons. On the other hand, non-metals like chlorine, they are easily reduced. So non-metals are oxidizing agents. So chlorine is an example of a good oxidizing agent because it is itself reduced, it gains electrons easily. Okay, now the next extra thing that you must know. So we just said that metals are reducing agents. Which group that you have learned contains all metals? If you think back to periodic table, you only learn group 1, group 7, noble gases. So which of these groups contains only metals? The answer, of course, is group 1. If you look at group 1, it goes from lithium all the way to francium at the bottom. Right? So this is the group 1 that you know, the alkali metals. All of them are metals. And you have learned reactivity for group 1 increases down group 1. This means that it gets more and more reactive. Lithium should be the least reactive in group 1. Francium should be the most reactive, most explosive. Now, this is what you have memorized, which the whole Singapore will also memorize. However, what does it mean for group 1 to react? How do group 1 metals react? For example, sodium, how does it react? Oh, sodium reacts with water, sodium reacts with oxygen, and so on and so forth. But how does it react with water? It reacts with water because sodium can lose one valence electron. So reactivity is ultimately linked to electrons. And we just said sodium loses electrons. So we can conclude, since francium is the most reactive, francium loses electrons most readily. If francium loses electrons most readily, it is the most easily oxidized because it loses electrons. If it's the most easily oxidized, that means it is the strongest reducing agent. So francium, being the most reactive group 1 element, is also the strongest reducing agent amongst the elements of the periodic table. So regardless of which element you are looking at, francium is the strongest, the most powerful reducing agent. This is because it loses electrons most readily and is most easily oxidized. So ensure that you take this down now. Okay, so now we will move from the metals, which is group 1, to group 7, which is the non-metals. So I believe the non-metals you are very familiar. Halogens. Group 7, right? VII is 7. So it goes from fluorine, chlorine, bromine, iodine, astatine, right? So these are the 5 halogens which you have learned. All right. And you have also learned reactivity of group 7 follows the opposite trend because reactivity decreases down group 7. So this you have learned before. So again, we are going to relate reactivity to electrons. So we know that group 7, they are all non-metals. Non-metals gain electrons. They are reduced, which means that fluorine is the one which gains electrons most readily. Of the group 7 elements, fluorine gains electrons most readily, which means it's the most easily reduced. If it's the most easily reduced, this means that fluorine will be the strongest oxidizing agent. And indeed, fluorine is a very, very strong oxidizing agent. Fluorine is able to react with every single other element in the periodic table. All right? And the main reason why fluorine is such a strong oxidizing agent is because it is most easily reduced. So now we have covered not just atomic radius, ionic radius, we have also covered metals are reducing agents, non-metals are oxidizing agents. And you must be able to explain this in terms of electron loss and gain. Now, something else that I want to cover also is that, okay, if you were to look at what I've highlighted thus far, I've highlighted francium and fluorine. Francium and fluorine will give rise to the most explosive, most vigorous reaction between two elements. Francium is the most reactive metal. Fluorine is the most reactive non-metal. All right, so let's just be aware of that. Francium is the most reactive metal. Fluorine is the most reactive non-metal. So if I put the two together, it should give rise to the most exothermic, most vigorous, most violent reaction. Okay, moving on. Now, how would you draw a dot and cross diagram to show the bonding in the compound form between sodium and sulfur? I believe you would have drawn this. Please, can I please encourage everyone? You need to be very careful. Some of you are totally not careful. All right? You like to assume it's covalent bonding. It's not. Whenever you have sodium, potassium, whenever you have a metal in the compound, it must be ionic bonding. So I was marking the time practice and some of you attempted to draw covalent bonding for something like sodium bromide. You should not be doing that. Sodium bromide is obviously ionic. Similarly here, sodium and sulfur should form an ionic compound. Therefore, you need to draw it like this. Next, if it's an ionic compound, please ensure you work out the charges of the ions. Do not assume that it's one sodium, one sulfur. It's not, in fact, because it's Na+, sulfur is in group 6, so it gains 2 electrons, so it's S2 minus. Therefore, it's Na2S. So you got 2 sodium, 1 sulfur. All right. Now, part E. Argon is also in period 3. Why is there no value for the ionic radius of argon? Ionic radius is a keyword. So I'm sure all of you will write things like, oh, argon is unreactive. Argon is a noble gas, full stop. Cannot. Or you write argon has a stable electronic configuration, full stop. Cannot. You must continue by saying this. This is the marking point. Argon is a noble gas with a fully filled outermost electron shell, so it will not lose or gain electrons to form ions. You must have the highlighted in yellow phrases. If you don't have these phrases, you will not get the mark at O levels. So please avoid just writing argon is unreactive, full stop. You have enough time to write more, please write more. Okay, and that concludes question 2, which is simply on periodic table, atomic structure, and chemical bonding. Okay, Now, if you look at the trends for the O-level TYS, so far, okay, bonding hasn't really appeared a lot. I mean, it does appear, but it's not a lot. So you might want to really focus and learn periodic table, atomic structure, and chemical bonding, and revise them together. These 3 chapters are all related. For those in my class, I've given you the summary notes. Please read them. Please commit them to memory. Everything. Okay? Now, moving on to question 3. Question 3 is more concept, quite clearly. Before you do any more concept, please underline the numbers and chemical names. You cannot highlight in an exam, but you can underline, all right, the chemical names and numbers. All right, Ken? Okay, there was a question about the previous part. Argon is a noble gas, okay? Noble gas is group 0. Halogen is group 7. So argon is not in group 7. Argon is definitely a noble gas, not a halogen. Okay. Now for question 3, please underline the numbers and chemical names. Next, you are expected to know that baking soda is sodium hydrogen carbonate. Now, how do you remember this? Well, you did the TYS. The TYS has a similar question. The TYS has this question in the 2015 TYS. So in the 2015 TYS, you saw that baking soda contains sodium carbonate and sodium hydrogen carbonate. All right. So how do you find the number of moles of baking soda used? First, you find the MR, then you convert 3.36 grams to moles. You do so by using the formula triangle M, N, MR. Okay. And if you do so, you will get 0.04 moles. Now, the next part is what I want you all to learn. Well, the next part requires you to identify the limiting reactant in the reaction. How do you do that? In the previous part, you have already calculated 0.04 moles of sodium hydrogen carbonate, so make use of it. The mole ratio is 1:1. This is from the equation. The balanced chemical equation tells you it's 1:1. So, 0.04 moles. This is from part A. Part A gave you 0.04 moles of sodium hydrogen carbonate. So if I have 0.04 moles of sodium hydrogen carbonate, 1:1 means I also need 0.04 moles of nitric acid for complete reaction. However, you are given 0.1 moles of nitric acid, which is more than the 0.04 moles required. This is the actual number of moles that is in the question, which is why I keep on stressing you must underline the numbers. If you have underlined the number, you will realize that nitric acid is 0.1 moles given to you. The equivalent is I've given you $10, but you only need $4, which means that nitric acid is in excess. There's more than what you need. And so, sodium hydrogen carbonate, baking soda, is limiting. Now, you need to know this. Okay, I told my class last year, limiting reactant is in the combined science syllabus. And for the past few years, it has only appeared in one MCQ. So it could also appear in structured. So you must be familiar with how to present your answers, which is like this. So if you are still unsure about how to present your answer for limiting reactant, please copy down and please learn from what I have presented here. All right, you always use the mole ratio, and then you use one of the numbers given to you or you calculated. The mole ratio tells you is 1:1. So 0.04, 0.04. Then, however, what is the actual real number of moles given to you in the question? The actual number of moles given to you is 0.1, which is much more than 0.04. Okay? Now, in this case, the 0.1 is more than 0.04 moles required. That's why it's in excess. But what if it's less than what's required? If it's less than what's required, then that reactant will be limiting. Okay? So this is a really, really important question to learn from. how to present your answer for limiting reactant. Okay? Okay, moving on. So once you have identified the limiting reactant to be sodium hydrogen carbonate, the next few questions are ultra straightforward. Why is it ultra straightforward? Because the limiting reactant is the one that goes into the mole ratio. You must use the limiting reactant. If you know that nitric acid is in excess, means the mole ratio don't care about nitric acid already, just care about the limiting reactant. And once you do that, finding the answer is easy. All right. So firstly, to find volume of CO2, okay, we will use the limiting reactant, sodium hydrogen carbonate, 1:1, and that gives you the 0.04 moles of CO2. After that, just use the triangle VN24 because CO2 is a gas. This is for gases only, remember? So the volume of a gas, you can just easily find it by taking number of moles times 24. All right. The mass of sodium nitrate, do the same thing. Use the mole ratio, sodium hydrogen carbonate to sodium nitrate, 1:1. All right. And that's how you get 0.04 moles of sodium nitrate as well. Then you multiply it by the MR of sodium nitrate. Okay. So I don't think this is very difficult. I think most of you can do this if you have the time. All right. And I think you understand how to do this. Now, if you don't know how to do this, it's very important for you to learn how to do this. Okay. Mole concept generally will pull your marks up. Now, the next thing I want to stress is please show working and statements. While marking your prelims, it was almost impossible to follow your calculations because you guys don't have statements. Statements means what I've highlighted in yellow. Volume of CO2, mass of sodium nitrate. If you don't have these statements, if you make a mistake in your final answer, I will just give 0. There's no method marks, no working marks, because I can't understand your working. And that has actually happened to students before. They just made one careless mistake copying from the calculator, and they got 0 marks out of 4 because no statements. No statements, I cannot follow your working, 0 marks, no method marks. So if you want to get method marks, please show your working clearly. Show the statements clearly. All right. You have enough time to write all these things in an exam. So please don't say that you don't have enough time. You do. Okay. Now, question 4. Question 4, these are the answers for the QA. I think it's quite straightforward. Okay. B is the first one you must start with. B is a gas that turns damp red litmus paper blue. This is ammonia. Now, this ammonia gas came from where? It came from A. A produced ammonia gas when it was warmed with sodium hydroxide and aluminium foil. This is a giveaway. Aluminium foil or aluminium powder is a test for nitrate. This means that A is some nitrate. What nitrate can it be? Well, let's look at the colors and the precipitates. A contains a nitrate and a metal. If I add aqueous ammonia in excess, it forms a white precipitate. Then you must be thinking, oh, but can be zinc, right? Can be zinc nitrate, right? No, because it's in excess. What it means is that the white PPT is insoluble in excess aqueous ammonia. That's why the white PPT still remains after you added excess aqueous ammonia. So which PPT is insoluble in excess aqueous ammonia? So you think back, you have learned zinc or lead. Must be lead 2 nitrate. The 2 is important. All right. Zinc cannot be the answer because zinc forms a white PPT, but the white PPT, zinc hydroxide, dissolves in excess aqueous ammonia. So in this case, must be lead 2 nitrate. All right. Then, if A is lead 2 nitrate, what happens after you add zinc powder? What kind of reaction could this zinc powder be? Zinc is a metal. Then you could ask yourself, lead is also a metal. Zinc, lead 2 nitrate. Zinc is a metal that is more reactive. So zinc is a more reactive metal than lead. So being a more reactive metal means this reaction that now takes place between zinc powder and lead 2 nitrate is displacement. Okay, so whenever you see that we are adding zinc powder, magnesium, calcium to a metal salt, you know that this is displacement reaction. So if it's a displacement reaction, obviously zinc being more reactive will displace lead. What it means is you form lead metal. So E is lead, while D will be zinc nitrate. So the nitrate now goes with zinc. Okay? Now, most of you will be thinking, oh, wow, suddenly so got lead 2 nitrate, got lead in the answer. Exactly. Lead ion is in your syllabus. However, we didn't do it during practical because Pb2 plus lead 2 ions are toxic. Having said that, even though it's not in practical, it can still be tested in theory, such as this. So just take note. I can test you on theory. And your batch is the last batch to learn about lead. Okay? The Sec 3s this year do not have lead in their QA. So this is another one of those examples of the last time they can test this kind of scenario. Now moving on. Once you have figured out that when you add zinc powder, it's actually a displacement, B part 1 and B part 2 should be doable. In particular, in B part 2, I've written zinc is a more reactive metal. The more reactive metal is on its own at the start, but at the end, the more reactive metal will grab the other ion for itself. So in this case, zinc grabs the nitrate over. On the other hand, the less reactive metal at first is part of a compound. Lead 2 nitrate is a compound. But because the less reactive metal is displaced, now the less reactive metal is on its own at the end. Now, this is what we call the chemical equation. The chemical equation shows you the full chemical formula of every substance present. Nothing is omitted from it. How will we write the ionic equation for this displacement? You need to know. So now we are going to do the same equation, but instead of writing the chemical equation, we are now going to write the ionic equation next to it. Please label clearly that that is the ionic equation. First, we start with zinc. Zinc is a powdered solid. Ionic equations must come with state symbols. So zinc, solid. At first, the more reactive metal has no charge. So it starts off uncharged, the more reactive metal. Then, how about the less reactive metal lead? The less reactive metal lead is inside a compound. The compound is called lead 2 nitrate. Lead 2 means what? The oxidation state is +2. The charge is 2 plus. So the less reactive one is charged at the start. Okay, so zinc more reactive, no charge. Lead Pb2 plus is charged. Then how do you end off? So now zinc forms zinc nitrate. To form zinc nitrate, okay, sorry, I left out state symbols just now. I'm so sorry. The state symbol for Pb2 plus is aqueous. And now zinc forms zinc nitrate, which is Zn2 plus. You know it's Zn2 plus because now it has taken the place of lead. It has displaced lead. Okay? So in zinc nitrate, you have Zn2 plus, NO3 minus. Now lead has been displaced. The less reactive element is now uncharged and is no longer aqueous because it's displaced as solid lead. All right, so you can see this is the pattern. The more reactive element, at first no charge, then at the end got charge. The less reactive one is the reverse, the other way around. All right, it was part of a compound at the start, so that it had charge because it was part of an ionic compound, but at the end it got kicked out, displaced, so now no charge. Okay, so going back to the displacement, okay, this is possible because zinc is more reactive than lead, therefore it can displace lead from lead to nitrate. Okay, I think this is quite straightforward. Now going to question 5. Now question 5 happens to be another metals question, which is about extraction of metals. So the idea is you need to read the information. Stage 1, what happens? Stage 2, what happens? Stage 3, what happens? So you are asked now in 5A, stage 1. Stage 1. What is the reducing agent? So you need to know reducing agents must be itself oxidized. So now you're going to look at stage number 1 and tell yourself which one is the one that is itself oxidized. I think it's quite clear cut. Carbon monoxide. Carbon monoxide is the reducing agent for stage 1 as it is itself oxidized. You must mention this in your answer. Don't just mention the oxidation states. All right. Once you have mentioned that CO is itself oxidized, then you go on to talk about the oxidation state of carbon increases from +2 in CO to +4 in CO2. Can you please ensure that you write it like this? It must be like this format. Try not to use other formats of answering redox questions. Okay? Now, once you have established that CO is the reducing agent as it is itself oxidized, the rest of the stages will make a lot more sense. In stage 2, calculate the oxidation state of sulfur in sulfuric acid. Show your working. So, how do you show your working? Most of you are so used to calculating in your head that you don't know how to show the working. Well, remember when I first taught you oxidation states, I told you, let the oxidation state of the unknown be X. So in this case, let the oxidation state of sulfur be X. Then you go and sub in. Hydrogen is +1, oxygen is -2. I have 2 hydrogen, 1 sulfur, 4 oxygen. All right. So once you have established all this, you solve for X, it's +6. The plus is important. Okay. Finally, in stage 3, suggest which metal, iron or manganese, is more reactive. I think it's quite straightforward. We just went through displacement. So you know that from stage 3, you can clearly see iron is more reactive than manganese because it can displace manganese from manganese sulfate to form manganese metal. All right. So I believe you can do stage 3 quite easily. But before we move on, let's go back to the 3 stages. If you look at the 3 stages, out of the 3 stages, which ones are redox and which one is not redox? I want you to identify which of the 3 stages are redox and which are not. Okay, so how do you identify which one is redox or not? You know that redox means there must be a change in oxidation state. There must be a substance reduced, substance oxidized. So stage 1 is definitely redox. Because we did in part A, we know there's a reducing agent, we know CO is itself oxidized. So it tells you that stage 1 must be redox. How about stage 2? Is it also redox? Okay, maybe we do a poll. Y'all can react, right? Tick. You can react tick if it's redox, cross if it's not redox. Stage 2. Come on, start now. Tick if it's redox, cross if it's not redox. Uh, can I have more responses, please? Okay, and the answer is stage 2 is not redox. So for those of you who chose that, great. Now, how do you know whether something is redox or not? The quick way is to remember what is not redox. An example of a reaction that is not redox is neutralization. And stage 2 is an example of neutralization. It's quite obvious, right? Manganese 2 oxide is basic. It's a metal oxide, so it's basic. Sulfuric acid is acidic, so it's acid plus base, basically. So stage 2 is acid-base neutralization. It's not redox. All right. Another example of a reaction which is not redox is precipitation. Precipitation is not redox as well. Now, finally, how about stage number 3? Do you think it's redox or is it not redox? Please poll now the same way, stage number 3, and show me, is stage number 3 redox or not redox? While I set up my charger. Not everyone has responded. Is stage number 3 redox or not? And the answer is, it's redox. Now, stage number 3 is displacement. Displacement of metals, displacement of halogens is a redox reaction. Okay, so displacement is always redox. All right. Now, this is important. Okay, for combined science, most of the time, they will not ask you something really, really complicated. But this could be one of the most complicated things they could ask you, which is this reaction redox or not? So it's important to know neutralization is not redox. Precipitation, also not redox. All right. The rest of the reactions will be redox. Now, moving on. Question 6. The entire question is about blast furnace. I don't think it's very difficult. I think most of you can do this. Now, again, another word of caution. Blast furnace, you are the last batch learning about this. Okay, the Sec 3, the new syllabus, doesn't have blast furnace, and therefore, it is important to learn the blast furnace well. And for context, blast furnace has not come out in the Section B essay since 2016. Last year, blast furnace only came out in Section A, about 3 marks only. Okay, so it's important to learn the blast furnace and memorize all the reactions and steps well in the blast furnace. Okay, now blast furnace is about extraction of iron. All right, so iron can be extracted from its ore hematite. Okay, in the blast furnace. So the first raw material is hematite. The second raw material is coke and limestone. The third one is limestone. All right, so HCl, hematite, coke, limestone. All right. Next, write down the chemical equation for extraction of iron. This is the chemical equation, and you should try to memorize this equation because this equation is honestly quite difficult to balance. Next, part C, describe how sand, the main impurity, is removed. Use chemical equations. I'm sure you can do this. You can just copy the notes, right? But importantly, please ensure that you write this in, whatever I've highlighted in blue. Calcium oxide is basic, SiO2 is acidic. Please write this in so that at least the examiner knows that you are aware this is actually an acid-base neutralization. And finally, state one advantage of recycling iron. I think by now we know the idea behind recycling metals is that it conserves the limited natural resources of the metal, of iron in this case. Moreover, if you use scrap metal, it reduces the waste that needs to be disposed of in landfills. Now, before we move on, there's definitely space on this page. Now, the blast furnace produces waste gases. There are some waste gases produced in the blast furnace, meaning these are gases that escape the blast furnace as waste. It's not slag. Slag is not a gas, right? Slag is molten, it's a liquid, it floats on top of the molten iron. So slag is not a waste gas. So what are the waste gases? Well, I'm sure you can imagine. Two of them are carbon monoxide and carbon dioxide. I think it's quite easy to understand where these two came from. These two came from, number one, CO2 is produced when the coke, reacts with oxygen in the hot air to produce CO2. But that's not it. The limestone also decomposes to form CO2. So this is another source of CO2 in the blast furnace, the decomposition of limestone. And the third source of CO2 is the actual reduction of iron trioxide. This reaction also produces CO2. So you have in total 3 reactions which produce CO2 in the blast furnace. How about CO? Which reaction produces CO? CO is produced when CO2 reacts with excess coke. So coke is added in excess so that it can produce carbon monoxide. Okay, so these are the 2 gases that will leave the blast furnace as waste gases if they are unreacted. However, there's actually one more waste gas which is even more crucial and important. And the last waste gas is actually this. Nitrogen. Where does nitrogen come from? Nitrogen doesn't come from a reaction. Nitrogen did not even take part in any reaction in the blast furnace. Nitrogen is just the major component of air. Remember, the blast furnace requires hot air to be pumped in. The hot air will contain, of course, mostly nitrogen. So there must be nitrogen that leaves the blast furnace. Moreover, nitrogen contains a N-N triple bond. This is the bonding present in nitrogen. It's a covalent bond, triple bond, and it's very strong. So if the nitrogen triple bond is very strong, it will be unreactive. And indeed, nitrogen, being the major component of air, is actually very unreactive. And that's why nitrogen can survive in the air without even reacting. Okay, so I want you to take down the waste gases in the blast furnace. There are 3 of them: CO, CO2, and most importantly, the major waste gas is actually nitrogen. Okay. Okay, and that concludes question 6. Let's move on to question 7. Okay, question 7 is about speed of reaction. Okay, now the test for the gas, I think I'll just leave it up to you to figure it out. The answer is there already. Now, this is about volume of hydrogen gas against time. So you are told that originally we use 1 gram of calcium lumps and it's added to excess water. Whenever you are doing speed of reaction questions, it is very important to know excess is an important word to actually underline, because it tells you that if water is in excess, calcium is limiting. Next, you are told this is at room temperature and pressure. So room temperature refers to 25 degrees Celsius. So now, if we carry out 2 further experiments, for experiment number 2, everything is the same, except 2 grams of calcium is used. Now, the effect of 2 grams means I've doubled the mass. If I've doubled the mass, I'm doubling the surface area to volume ratio. Okay, we have gone through this in class before. If I double the mass, I double the surface area to volume ratio. That is the first point. Now, if I double the surface area to volume ratio, this means the speed is faster. And how would you show on a graph that the speed is faster? The speed is faster if it's steeper. So I've just drawn that for you. Next, because I have doubled to 2 grams, this also not only doubles the surface area to volume ratio, this also doubles the number of moles of calcium. And we know calcium is limiting, so it will double the volume of gas produced. So what it means is that now it needs to produce double. Okay, just give me a minute. Let me draw nicely. So it's not random, people. It cannot end off anywhere else. It must end off at double the volume. So it's both faster and double the volume of gas. Now next, experiment number 3. Everything is the same, but temperature is increased. I think this is quite straightforward. Okay. It's just steeper, but it ends off at the same volume. So this is experiment number 3 in red. Okay. Okay, maybe you want to draw it steeper and nicer. Okay, I'll leave it up to you. Okay, like that. Okay. Now, I want to go through experiment 2 in greater detail just now because I think that's what a lot of you will be very confused. When you double the mass of the lumps, you double the surface area to volume ratio as well. And therefore, it's steeper, it's faster. And you also increase the number of moles of limiting reactant. Therefore, you increase the volume of gas. Okay. Now, this kind of graphical interpretation questions, you must be familiar with it. To be really honest, if you look at the O-level TYS, it has not come out. For the past few years, it has not really come out in the structured paper. Therefore, you must be very, very familiar with how to draw these graphs yourself. Okay? Now, finally, besides increasing temperature, besides using a greater mass of calcium, another method to actually increase the speed, obviously, is instead of using the lumps, use powdered calcium. Now, when you use powder, the particle size is smaller. Particle size means how fine is it? Powder is very fine. It's not coarse. It's not a big lump. All right, so it's smaller particle size. If it's smaller particle size, it has a larger surface area to volume ratio. Now, I know my notes only wrote surface area. I think let's learn the full term, larger surface area to volume ratio, which is also similar to what the bio students will always use in bio. This is the concept from bio, surface area to volume ratio. So the surface area to volume ratio exposed for reaction is greater when you use powdered calcium, and therefore it increases the frequency of collisions, hence the frequency of effective collisions between reactant particles. Don't forget the between reactant particles when you are memorizing the explanations. Okay, so that concludes question 7, which is speed of reaction. Then we go on to fermentation. This one, I shall leave it up to you to read yourself mostly. I think it's not very hard. Most of the questions you are familiar. However, if you notice, there's a very interesting tube containing water in this case. Usually, we will bubble the gas into lime water, not water. So what is the purpose of the tube containing water? Now, the purpose of this tube is the same as the lime water, which is to act as an airlock to prevent oxygen in the air from entering the setup. Okay, if you don't have this tube, then the oxygen can enter and oxidize the ethanol to ethanoic acid. So this is the one that I think most of you don't know. What is the purpose of the tube containing water? The function is the same as the tube containing lime water in our notes, which is to act as an airlock to prevent oxygen from entering. Okay. Next. Now, D part 1 and D part 2, please star. If you can star 3 times, that's the best. Some of you say, oh, Mr. So never teach. Right. Did I really not teach? Okay. Think about D part 2. How would you obtain pure ethanol? The answer is fractional distillation. So fractional distillation is how we will obtain pure ethanol or concentrate the ethanol from the mixture. In organic chemistry, when you're asked to purify something, it's usually fractional distillation. However, for D part 1, why is it filtration? The cloudiness is due to the yeast. Yeast is a powder, you know. You usually buy yeast powder and just add it in. The bio students should know that by now, right? So how would you remove yeast powder? You just filter it, filtration. All right. Now, this is important. I've mentioned this in class before. The use of fractional distillation to purify and separate the ethanol from the mixture for fermentation. Please learn it. All right. And I think finally the equation is easy. Okay, I don't think this is very hard. Okay. Now, if it helps you, please go and memorize this equation as well. It may be difficult to do this from scratch, especially if you forgot the formula for glucose, C6H12O6. Okay? Now, up to this stage, this is section A. Section A is 45 marks. Our target here should be to score 35 at least. If you want to do well, you must score 35 at least. And when I say do well, I don't even mean distinction yet. If you want a distinction, your section A should be something like 39 out of 45. All right? So you must be averaging 39 out of 45 consistently if you want a distinction. So let's aim for excellence, aim to go from good to great. Make sure you give yourself time to think through and write complete answers. But next, it's equally important to do well for section B. If your section B is only about 12 out of 20, you won't do very well. You need to aim for something like 14 or 15. 15, honestly, is the target grade for section B out of 20, which means that section B, you must leave 30 minutes to do it properly. So during your exam, let's say your exam starts at 2:30. You can only do section A until 3:15. 3:15, no matter where you are in section A, you must go on to section B because you need 30 minutes, half an hour for section B to do it well. And section B, most of the time, is just regurgitation. Therefore, you need to leave time for that. Please look at question 9A and B. A and B are just simply regurgitation, right? These are things that you have studied. You can just apply it immediately. So what are two unique physical properties of potassium metal? Unique to potassium, unique to group 1. So you must choose something unique, such as soft and easily cut. That's one property. Low melting point. So group 1 metals have low melting point. Low density, also for group 1. Okay? And finally, for today, draw the electronic structure of a potassium atom. So I hope you know by now, atom means it has not lost electrons yet. If it has lost electrons already, what do we call that? If it has lost electrons already, we will call that what? Ions. Okay? So please know the difference. If it hasn't lost electrons, it's called atom. If it has already lost it or gained electrons, it's an ion. Okay? Now, I shall leave it up to you to read the rest of the answers, which I've mostly filled in for you already. All right? Some of the answers I didn't fill in for you. We will continue tomorrow. All right? I don't want to continue too late. But I hope, okay, you realize that actually organic chem is important. Because section B, okay, there usually will be questions on organic chem. Now, if there is organic chem in section B, try to do the organic chem question. Organic chem is rather standalone, and if you have studied organic chem thoroughly, you will be able to do relatively well for it. Now, I cannot guarantee that organic chem will definitely appear in section B. I cannot guarantee that. However, if it does appear, choose organic chem. All right? That will usually help you. Okay? Now, at this point, I've ended my review for today. We will continue tomorrow at the very same time, 8:30 p.m. All right? Let me stop the recording now. Thank you.